Hello, everyone. My name is Kyle Schwiebert, and it's my pleasure to talk today about higher order models for turbulent fluid-fluid interaction problems. Before we get into fluid-fluid interaction problems, perhaps just a couple words about what fluid flow and turbulence are. So turbulent fluid flow is that flow regime which is unpredictable, hence the word turbulent. So there's laminar flow where it sort of behaves more predictably. The flow lines are all next to each other, but in turbulent flow, what we instead get are these vortices which form. And it turns out that the smallest vortices, they're small vortices, these whirling flows, the smallest ones are what dissipates the energy. And so if we're not modeling what's dissipating the energy, then energy is going to build up in the system and we're going to get a result that's not good. But it turns out that those small vortices are actually too small to model. So in comes LES and LESC turbulence models, which stand for large eddy simulation and large eddy simulation with correction models, where instead we just sort of average the effect of these small vortices. We model vortices of scale or size delta, and we sort of average their effect on the system. But here we get into trouble again, because we're averaging with respect to this delta. And if we make delta too small, then we're sort of recreating our problem. So we're trying to model scales which are really too small for us to model. So we can't decrease delta, but we'd like to get higher accuracy with a larger delta. Enter LESC models, where we model the dissipation, and then maybe we're cognizant of where our dissipation modeling went wrong, and we try to correct for it, solving our system again. Okay, so that was turbulent flow. Let's talk about fluid-fluid interaction problems, specifically with a rigid lid. So this is a proxy for atmosphere-ocean interaction. So we have omega-1, which is the atmosphere domain, and we have omega-2, which is the ocean domain. And we have I, which is this non-moving, hence rigid lid interface between the two. For completeness, I list the equations here. The first one is the Navier-Stokes equations in either one of the two domains, and then the second equation and third equation describe the coupling conditions. Following three just sort of close the system. Okay, so we're solving these problems on a computer, right? If we knew the perfect solution, we wouldn't need a computer. We want to approximate the solution, and for that, we need a computer. So what would we like our numerical model to do? First of all, it should be decoupled. We don't want the system to take too long, and it turns out that a decoupled solver takes a lot less time than a coupled solver. That means we solve the ocean and atmosphere separately and put the solution together rather than solving it as one big system. It's about 4 times faster. Next, we want a solver which is unconditionally stable. An unconditionally stable solver is one that gives us a physically meaningful solution, so the velocity doesn't become faster and faster over time. Thirdly, we want a system that's valid for turbulent flow. That's sort of our whole goal here, is having a turbulence model for fluid-fluid interaction. Lastly, we want a solver which is higher than first order accurate. What do we mean by first order or higher than first order? Well, a first order scheme, as you double the amount of computational effort, you only get a scheme that's twice as close to the real world solution as what you had with the base rate of computational effort. If we have a second order scheme, then as we make it twice as computationally expensive, we actually get a 4 times better answer to our problem. And if we make our problem more difficult to solve multiple times, then pretty soon the second order solver way outpaces the first order solver. All right, so a quick history of methods and how they were able to achieve these benchmark properties on this problem. So first, sort of the monolithic model is sort of the first model one might come up with looking at those equations. And unfortunately, it's not decoupled, it's not stable, it can't handle turbulence, and it's first order, it's not high order. And in 2012, geometric averaging was introduced, which stably decoupled the problem. So it's stable and decoupled, but it can't handle turbulence and it's not high order. Then there came a scheme that could handle turbulence, but was not stable. And then with my collaborators in prior work, we came up with a decoupled, stable model that was capable of handling turbulence, but was still first order accurate. Finally, with this grant, we came up with NS omega C with geometric averaging, which is decoupled, stable, can handle turbulence, and is second order. So here's just a brief image on a model problem illustrating what I mean by second order accuracy in another way. So we can see how much steeper the error decreases for the NS omega C model versus the NS omega model. And you can see that after a few more iterations of increasing the computational effort, we end up with a solution that is much more accurate than the solution we started with. Note the log scale on the error here. Then we have flow past the cylindrical obstacle. This is a more real world problem, let's say. So we have the atmosphere flowing in from this side of the domain, and we're expecting that as it tumbles over this obstacle, it would induce some flow in the ocean. Right? So the atmosphere sliding past the ocean should cause the ocean to pick up some of that energy eventually. But in this NS omega model, which I'll remind you again is the second best of the ones we discussed, completely fails at noticing this energy transfer to the ocean domain. NS omega C, on the other hand, thanks to its additional accuracy being second order rather than first order, is able to predict correctly that there will indeed be some energy and therefore flow transferred into the ocean domain. So in conclusion, we have successfully built up a model of atmosphere-ocean interaction that can be used successfully with turbulent flows. The scheme's higher than first order, while still being a decoupled scheme and unconditionally stable. It's important to note that this scheme is first of its kind. Here are my references, and at this time I'd like to thank you for your attention and acknowledge my collaborators, Mustafa Aggul, Alexander Labovsky, my PhD advisor, and Onal. Thank you.